Okay, so I will come to the third lecture. And this lecture is mostly about homology of models. Study the homology of moduli. Then we both can recall that this is MS is defined to be quantifying space and the reason that we care about is that elements in these homology groups correspond to characteristic classes of variable numbers. So, well, of course, for full manifold, a complete understanding of his homology is still out of reach, but what we can do is try to get partial information using Seiberg-Witten Invariants. Yeah, and one thing is maybe I forgot to mention that in a special case, for example, if X is not full manifold but a Riemann surface, so there is one can study B if of X. This version of moduli space is not quite the moduli space of complex structure or hyperbolic structure, but over rational, yeah, so moduli space. For example, complex structure. So if you for example, so if you refer on rational homology group, then you can use just no problem. Okay. So okay, and now over this moduli space we have a universal boundary. That's and so I want to there is a specific family of homology classes which are especially useful. Let's call it the generalized class. So how do we do that? So let's say apply. So we have this T vertical tangent bundle. This vertical tangent bundle. This is just this is a vector. By putting a metric, we get it's classified by an element. That's helpful. It's classified by a map from this. Sorry. So classified by the map, but from maybe I just roughly do that. You to forward. So one thing we can do is okay. So we do. I'm going to know this man by row. Okay. So we can do one thing we can do is we can start with talking about the elements in this let me use breaking. Okay, then we can pull back using row that give us elements in the auto space of this. Right, now we can do fiber integration. is united for times. Of course, here you can do like you can use other coefficients, d or d2, that's fine, but for now let me just do expression. And this so with no image of this map first. Well, now if the knowledge structure of this is the polynomial in U1 and E, right? So this is just the first conjugate class, the Euler class of the universal one. And just say we know this map basket. So we know an element. So if we have an element C here, we know the image. Okay. So this is the generalized word in the manifold class associated to a characteristic class of vector class. So in other words, if you have a characteristic class of vector bundle, you can take this class for a vertical tangent bundle, get the homological class of the total space, and you do fiber integration, and that give you the homological of the base. Okay. Yes. And so one thing we hope to, let me just focus. So we make the solutions. Now this is for the technological limit. Homological ring. It's the subring generated by image of namely it's just in other words it's just generated by this upper process T1 30 is equal to B. Okay. But let's do it. Yeah. Okay. So yeah. So basically, as I said, it's for four manifold, it's not so it's completely determining computing this guy is out of reach. But at least we can somehow try to understand a smaller subring, which is the subring generated by these Morrison multiple classes. At least we know about the generator. So the point is to find out all the relations in order to determine such subring. Okay. And so maybe let me do some examples. So what are the examples? See. Yes. X is X. Okay, so what's your favorite of all these? First B, right? Yeah, first here, okay. Yeah. Now okay, so the first fundamental question is what do we know if answer? Okay. Well, this is a fundamental question. And until a few years ago, answer is nothing. Nothing. Okay. But there is a recent breakthrough. Well, not so recent, but 7 years ago, by Watanabe. So which I will briefly talk about. So basically, okay, what do we know about some basic property of this group? So we know Okay, so first of all, we have a map. We can consider F05, which is the isomorphic. We have the inclusion. Okay. And have inclusion. We also have an inclusion from both groups of four-dimensional grids. That's what you just extend by n. And what else do we have? Okay, we also have graph and feed F4 to the frame bundle of. So what do we mean? Here frame means just framing, not autonomous. We don't require. It's just a. So it's a point in this space is just a point on S4 and the basis of its tangent space. Okay, how to do that? It's just like F then takes F to F star of the function. Well, I goes from before here E1 before is the standard difference of T0. Okay, we have this map. Okay, so well, what's this? This is form of equivalent and so far. So using this, you can actually, it's not hard to prove that. When I say we know nothing, we know something. We know something basic, which is each at force is homotopy equivalent to D4 cross SO5. Okay. I mean, these two spaces. You can build in maps in both directions using this two. Yes, okay. So therefore, well, now the thing is that we don't, and the amazing thing is theorem. Saying that before it's not trivial for values are fine. I mean, starting, I guess I was one. I don't remember. And the first, this group has another thing about that group. So in particular, so okay, from this we see that the speed is still is equivalent. This D4 minus this BSO5. Okay. So using Quintet's formula, we see that the moduli space, the homology of the moduli space for S4 is essentially come from this homology, this SO5 and this part. Okay. But it turns out that not hard to prove. That when we just focus on the topological ring, so when we focus on topological ring, we are just studying like this generalized MM classes, this nonlinear part. Basically, you can treat this as nonlinear part and a linear part. But when we focus on the topological ring, it's not hard to prove that this nonlinear part doesn't play any role. We can just pretend that this space is two. This is you can try to do this by yourself using Merrick-Bush. So let me give you the conclusion and the fact. So what's the fact? The fact is that okay, so we have mentioned, remember that we have this map from if S4 to SO5, let induce the map from H star of B SO5 diagonal to H star say turns out that this the image of this induced map lands in logical ring X4 6 inside. Yes. Well, this is just this. Let me call this one. The image of power star is exactly the topological ring. And this sense, we know about this. This is just polynomial ring generated first contact path. Ask a quick question. Why don't we have a point? Yeah, fine. That's fine. Yeah, so rational coefficient. Question. But the class have a little send to P1. So under this map, P1 out from P1 equals the top class of P1 E of 2 and alpha P2 equals P2. Two here essentially because all the numbers series. Yeah, so you can prove this using language. That's not too difficult. As a result, so the topological ring S4 just equals a polynomial ring to two variables and two free generators are just the kappa class of P1 and kappa class. Okay. Essentially, that's because this series is a polynomial.
Well, what's the image of P2?
Image P2 also kappa P2 over 2.
We have P2.
Well, P2 is just EQ. So you can just go EQ, kappa EQ over 2. Okay. Kappa EQ over 2. Oh, sorry, so I should say this should allow maybe P2 is just P2 is squared. So P2 is just so the homological ring of S4 is polynomial ring. It's so from here we see that although the diffeomorphism group of S4 can be really complicated, the topological ring is relatively easier to understand. So really it just focuses on those linear characteristic classes. Okay, this is the principle, and now the next hope is to understand what about the topological ring of S2 of S2. Logical ring of space surfaces. And you can write off your favorite examples, right? But it turns out these are only partially known. We don't have a complete computation of the topological ring of these basic, very basic methods, which is unfortunate. Well, fortunately, unfortunate, and interesting things to think about. So, for example, I think the solar pressures and centrifuges, they have a lot of work in this direction. And so today I want to present a plot by David Bauer, which essentially says, okay, let me just say we completely computed the topological rings of CP2. This is just a rational polynomial G n square. And also to represent CP2. Only some fringe polynomials. And also I think there are some terms topological in X. Let me see. X is static. Potentially, he find out an approach using Seiberg-Witten theory to get like inductive computation of the topological ring. And as the Beatty number increase, the computation gets more and more complicated. But he was able to successfully completely compute the first two cases. And also I think his approach has further potential to solve more cases. And maybe so I guess I will spend some time discussing the proof of these results. Okay. Yes. Okay. Any questions?
Maybe not an important one. How far have a completeness return?
Subjective to what? Subjective to
The monogeometry multiply.
I would say never. Yeah, probably using what happens for if I can show that any x is there are some characteristics which are not in the count. Well, yeah, not so. Well, probably what I show that are some. At least my expectation is that any x are some is strictly smaller than 1.0. We will see some construction of, for example, we will construct some characteristic class using Seiberg-Witten theory. At least we know that one do not land in the image of. So basically, again, so the idea is that these are kappa classes are linear version of the characteristic classes. Okay. All right. So what do I say? Okay, yes. Now, okay, I want to expand a little bit on this result. Before I do this, I want to make a digression into Donaldson theory, which is not Seiberg-Witten theory, because actually, because it's very relevant to the problems. So digression, which is Donaldson's proof of diagonal definition. Using AXC. Okay. This is not Seiberg-Witten equation, but it's any self-Yang-Mills equation, and I'm going to briefly discuss Donaldson's proof, original. Okay. So yeah. So what's the setting? X is non-manifold. The I1 of x equals simply connected, and the same equal of x equals 0 is negative definite. And we are hoping to prove that the intersection form of x is diagonal standing. Okay. And how to do that? Okay. So well, Tom already talked about the proof using Seiberg-Witten theory, right? So I'm going to do the proof using Donaldson's theory. So here's what I'm going to do. I will sketch a proof using Donaldson's theory. I will try to generalize this proof into a fake proof of this theorem, then I will say something about the technical difficulty in making this fake proof a rigorous proof. Then I will return to Seiberg-Witten series and say something about like how to modify Tom's proof into a family version and prove this. Yes. So we are going to jump in between these two series in order to have some information on what's happening, what's really happening here. Okay. Right, good. So yes. How to prove this? Let's consider a principal SU2 bundle over OX, which satisfies C2 of X paired with whose second term class paired with X equals yes. You can, it's not hard to obtain such bundle by taking a line bundle and taking the direct sum between this line bundle and it's still. Okay, so now take or you can just take a degree 1 map from X to S4 and pull back a SU2 bundle from S4 with CP2 with C2 equals 1. Okay. Yeah. Now how do I do it? Okay, yes. And now we can try to study the moduli space, ASE moduli space on X. So this moduli space contains a connection A on P, which is satisfied. Its curvature is P. Consider a connection. Its curvature is a two form whose value in the Lie algebra from and whose value is a two form with Lie algebra value. And we can take its self-due part will require that it's 0. You have seen it in the Seiberg-Witten setting. Only difference is that P is a SU2 bundle, not the S1 bundle. Okay. Now, of course, we still need more about gauge transformation, which in this context means the automorphism of the principal bundle. All right. Yes. So this is the anti-self-due moduli space, and it has two parts. So M and C. It has the irreducible part and the reducible part. Okay. So what does irreducible mean? What does reducible mean? So here reducible means that A can be solution A such that A can be split into A L and some A. Well, L is so what's L? L is a line bundle, complex line bundle over your fundamental X this you can direct sum this line bundle with its dual bundle. Maybe I will just with its dual bundle you get this SU2 principal bundle. Okay. So yeah, sometimes the connection, sometimes this SU2 bundle can be split into a direct sum of two complex line bundle, U1 bundle. Okay. In other words, the structure group can be reduced into U1. And we say a connection is reducible if it is really just split into two U1 connections. Okay. Yeah, and of course we require and now using the condition that D plus equals 0, it's not hard to see that whenever you have such a splitting, you have a unique reducible solution. So this is really just the set of L such that a set of line bundles such as L direct numbers. Oh well, that might. But here there is a finish. You can replace L by L. And such thing is the same as this homology class. The string of x square equals -1. Because this C is just first term class of L. And of course, we want to know something. Okay. In other words, we are just looking for homology class, integer concentration of homology class, whose square equals -1. And we're just looking for pairs of, we're just looking for such homology class. Any such homology class will give us a reducible solution. Okay. So we have finitely many reducible solutions. What else? Near each of these. So let me just say, let me just call it AC. Okay, C is near each AC. Near each reducible solution. It's one can prove that this so what else? Oh, okay. So for neighborhood, small neighborhood class is useful. It's just so locally, so reducible means, okay, so what do we mean by reducible? Reducible means gauge group do not, it's fixed by some gauge transformation, right? And what's the gauge transformation here? It's just a gauge a constant gauge transformation on AL. Okay, so let's S1. So the isotropy group of a reducible solution is S1. So locally, this moduli space locally looks like C3. C3 comes from the kernel of the any self-field Yang-Mills equation of the linearized ASD equation, which is think about like implicit functions here. So we are trying to solving an equation. Locally, it's just the tangent space just kernel of the differential. Okay, so this is C3, and you need to mod out by the circle action because it's a reducible solution. Okay, so in our world, this is just a different union of C such that C squared equals -1 plus 1 form over C. Okay, this is one feature. Another feature is that M reducible whereas this is non-compact. Okay. The reason that it's unlike Seiberg-Witten equation, this Yang-Mills equation moduli space is non-compact because it's bubble phenomenon. This is conformal invariant, so it's possible that a sequence of solution have energy which concentrate to a single point in this case. You cannot have bubble in multiple points because C1 equals 1. Okay? You have no energy to do more than one bubble. You just have one bubble. Okay. And as a result, but this is not compact. However, we can do all of this thing. Application. We add in those ideal solution. This is just union. Okay, so let's think about this. So this is our manifold X, and we just have one bubble, right? So after you remove this bubble point, you can extend the solution through this point. This procedure gives you another solution, but since you remove a bubble, it decrease the instance number by 1. So now you just have a ASD connection on a trivial SU2 bubble, which is just a flat connection. And now we can use our assumption that pi1 equals 1. So in other words, so the limit is just like this is the ASD solution of S4, and the other part is just trivial connection. Okay, and this we need to record this the position of this bubble, and as a result, we are just adding in. Okay. So this is a 5-dimensional moduli space, non-compact. Okay, it has 2 features. One is non-compact, but we can compactify it by adding a copy of the manifold itself. Okay, because it's just we're just adding like the position of doubling. Okay, so this is one feature. And the second is it's not really a manifold, it has some singular point. Singular points correspond to these cones on CP2. Okay, so we have this is a 5-dimensional manifold with singularity, with very well controlled singularity. Okay. All right, now what do we do? Now, okay, beautiful. What we do is okay, we just remove a tubular neighborhood of this singular locus. Okay. This provides us this is a 5-dimensional topology from this union of C bar, because we need to reverse because we want to treat it as a commodity. So we want to reverse the orientation in coming n to this our negative definite for manifold S. So this is a 5-dimensional commodity, right? So okay, so now we know from algebraic topology if 2 4-dimensional manifolds are coordinate to each other, they should have the same signature. Okay. And what does that mean? That means A implies the signature of this guy is just this. Okay, so that means the elements in X squared equals -1 equals twice the rank of because there's this twice here because we are just modding out by ±1. Okay. And it's not hard from here to see that this implies the intersection form must be 5-dimensional. Because otherwise this number will be you won't have so many unident vectors. Okay. So let's follow this proof. Okay, why do I want to talk? Why did I talk about this? You may want. Well, this is a beautiful argument, but you may wonder why. Why is it relevant? Okay, good. Now let's try to do it in a family setting and see what happens. Yeah. So far, any questions? So far?
And so why do we have a one copy of X of these?
Yes, because okay, so what do you mean by a bubble? Bubble means a sequence of solutions. And the word doesn't really have a limit. It's okay, so bubble means okay, if we have it's possible that you have a sequence of solution of this energy concentrated more and more at one at like a bunch of points. And when you rescale, this ASC equation is conformal measure. So you can rescale near this point, can get a solution on S4. Really on R4, but you can complete it S4. So basically, this Uhlenbeck compactification, this procedure just recall the constant point of this of energy. In general, of course, they may be more than one constant point. But since C2 equals 1 in this case, you just have enough energy to bound once. And the rest, so basically what happens is that you have a sequence of solution whose energy can converge to a single point. After you do a suitable rescaling, you get a sequence solution. So R4, which can be again completely equal solution of S4 with C2 equals 1. Okay, so let's one this. And for the rest, the energy is just 0. So it's just a flat connection. But your manifold is simply connected, so it's just a trivial connection. So the only information of this limit is just this position of bubble, which is a point on S. So therefore, this compactification is just adding those bubbling point. It's like it feels like a little like quantum McPherson. Yeah, yes. So always wonder if there's some mysterious connection here. Yeah. Yeah. So so with adding this ideal solution, which is the limit of such convergent solutions, that give us a compactified 5-dimensional with boundary. Boundary is just the original manifold X. And we also have some singularity coming from the reducible solutions, which are just cones over CP2s. You remove this singularity, you get a cobordism from copies of CP2 to X, and they should have the same number of signature, and they give you this algebraic condition and conclude that this intersection forms is bad enough. Okay. This is really beautiful. And now let's try to do it in a family setting. Okay. So family setting. Now let's do E. Okay, we have E over what? Let's consider E. You have this X. X is we have a small spiral bundle over E. X is again X is speed club equals 0, 1 equals 1. Actually, you can just assume X is bunch of CP2 bar connected sum. We're trying to classify CP2 bar bundles. Okay, but let's yeah. So X satisfy these conditions. To make our life easier, let's assume the base X trivially on the homological side of the fiber. It's yeah, let's simplify the argument. So now let's try to carry out this proof, the family set. What does that mean? Okay. We consider a principal has Euclid bubble. Okay. Which satisfies the first second class pair is next B. Okay. Then now we can study this NCLQ. Well, now we can study this This is just pairs A, little B and A. Well, B is the point in your place. A is a connection on P with 2 plus B. And of course, we need to if it satisfy the S equation. Okay. And of course, we will work out the gauge information. Okay. So this is just parameterize the moduli space of ASC connection. Okay. Yeah. When B is a single point, we'll just return to the original set. Okay. All right. So okay, we can do similar things. Again, this has the composition into the irreducible part and the reducible part. Okay. And now what's the reducible part? The reducible part So let's see what's the reducible part. In when B is a single point, the reducible solution, you just have the discrete reduce. You just have a bunch of discrete reducible solutions, right? But here B is but in general, for general B, this is just E cross C. Let's C squared equals -1. So whenever you have a decomposition, so because note that on every fiber there is one with okay for any point in the fiber and any homological class which satisfies this condition, you have one reducible solution. Right. So that means that if you take this, if you take a union of solution, reducible solution over all fibers, you just get this product space. Okay. And moreover, this so here this E cross C, this the moduli space is modeled by what? This moduli space, this parameterized moduli space is modeled by VC of proportion S W, where VC is a three-dimensional vector bundle over basically it's what? It's just similar to here, right? B is a single point. Now you have a vector bundle because really the fiber is just the kernel of the linearized Yang-Mills equation. So you have a fiber bundle. You have a vector bundle here. It's important that it's a vector bundle. Okay? Because you're just taking the kernel of the differential. So it's a vector bundle. And near the reducible locus is modeled by this vector bundle, which has one. Okay. Now we can also do the Woolenberg compactification. Now what do we want to add? What do we want to add? What's the boundary? E, right? For each fiber, we add on each fiber, we just add the fiber. So take the union of all fibers. It's E. Okay. Good. Now, we play the same game. We remove this tubular neighborhood of reducible solution. Let's give a homologism from showing union of E plus C squared equals -1 PVC. PVC means VC is a three-dimensional vector bundle. So you can take its PVC is just associated CP2 bundle, projective space bundle. And because we want to use this as an incoming end, so I have to reverse the orientation. So this is the incoming end, and the outgoing end is E. Okay, we get a cobordism from these projective bundles of vector bundles to E. And moreover, this cobordism has a map in E, right? Because it's really just union of your moduli spaces over different fibers. Okay, so that's the structure. We have a bunch of more structures, but let me not go into too much details about that. Basically, the thing I want to conclude is that from this one can expect that when computing. Okay, so what do I want to say? Basically from this one can expect that the kappa class of let me just write T1 of our original bundle equals the sum of this because you have a cobordism, so you can use Stokes theorem to conclude that the kappa class of this bundle is just the sum of the kappa classes of its CP2 bundles. Okay. But what's special about these CP2 bundles? These are not random CP2 bundles. These are projective bundles associated to vector bundles, right? So, it's hard to classify a general CP2 bundle because the structure group is in diff CP2, which is complicated. But these bundles are much easier to understand because they are just projective bundles associated to rank 3 vector bundles. Okay? So this provides us with a way to compute the kappa class in terms of this projective space bundle associated to vector bundles. Okay? So that's the idea from Donaldson theory. And I say it's a fake proof. Why is it? Well, the idea is beautiful, but it at least in Barelia's paper, he did not follow this. Well, he described this intuition from Donaldson theory, but the actual proof doesn't use Donaldson theory. The thing is that I treated a lot in this process. For example, how can we assume this parameterized moduli space is a manifold away from no singular point? We need to choose a generic metric, and for a single manifold, it is doable. I think it's work of Uhlenbeck and many others. You can choose a suitable metric to make the moduli space nice. But in a parameterized setting, I don't think we want to do that. So this is just an intuition or proof. And now let's go to the actual proof using Seiberg-Witten theory. I think I have. When did I stop?
I have so you have 7.
Oh, great. Okay, so I will go to the Seiberg-Witten proof. Okay. So but I like this fake proof because it provides a lot of intuition. Why is it true? Because you can play this game to get a cobordism from your nonlinear CP2 bundle, nonlinear manifold bundle to a disjoint union of linear projective space bundle associated to vector bundles, and whose kappa classes are much easier to compute.
Okay, but is it not known, or is it for them? Is it not? You could in principle find a genetic matrix for each.
It's not.
Okay, so potentially it's not fake proof.
Potentially it's not a fake proof. Yes, if one works hard enough, and yes, but there are some technical challenges which is not overcome yet. But yeah, if someone is motivated enough, it may be an actual, even maybe made into an actual proof. And actually, I would say this approach has a lot of potential. Like you can consider like modular space for higher instance, and you can try to use this to develop like family version of Donaldson invariants and study diffeomorphism group. I would say yeah. So all these are things that are interesting, but not many people. But yeah, anyway, so yes, now let's go to the Seiberg-Witten theory. Okay, so
the projective bundle thing, like the C's there can be fewer components.
C, no, I mean it's the same. The number of components must equals to
Oh, 21x trivial.
yeah, here I'm assuming power x trivially. If you assume power x non-trivially, one can modify this argument. Still get something similar. Okay, so now let's go to the Seiberg-Witten equation. So now the Seiberg-Witten proofs. Okay, so we have a let's start with assumption. So bundle and we'll take the family into structures. Okay. And then what do we do? Okay, we have the family of 3 times 11, okay, which comes from the finite dimensional approximation of the family Seiberg-Witten invariant. So what is it? So it's really is a map from the home space of the what was my notation? We got the minus. Okay. It's a map between 2 home spaces, which satisfy B plus minus B minus equals what? Equals the index bundle of the P1 operator. We don't have the hot star operator in this case because B plus equals 0. So just have P1 operator. Because that H plus bundle is true in this case. Okay, index. This is the index bundle of the family P1 operator. Now I'm going to write it as element of this because it's a complex. It's a complex linear operator. It's a family of complex linear operators. Okay. This map, what does it satisfy? It's just one divided. And second, it's so it is a homomorphism. As one. Because if you take the S1 fixed point, you are really just starting the Seiberg-Witten map on reducible solutions. And in this case, the reducible solution, the Seiberg-Witten map is something like FA plus minus sigma 5, something like that. Now, reducible means this term is down, and the DA phi is phi is 0. So this term we just have this FA plus, but B plus equals 0. So this is the isomorphism. So that means if you restrict this map to S1 fixed point, which is okay, the S1 fixed point of this term space is the term space of the real part of B plus. Okay? And this S1 fixed point of this is the term space of the real part of B minus. And here I'm just saying that when passing to S1 fixed point, it should be a homomorphism because it's induced by a bundle isomorphism. Okay, and from this, one can, by some computation, one can conclude that this yes C1 plus CED of this index must be 0, then I greater equivalent. Let me see what's the for any I greater than S, which is sorry. This means the numerical index is an integer. So it's the virtual dimension of this. This is non-trivial. Why? Because here, how do we define C? How do we define the term class of a virtual bundle? It's just you take the term class of this bundle, you formally invert the total term class of this bundle, and you multiply them together, right? Then so it's not obvious at all, like why this is. I mean, if you don't assume such map exists, then this is certainly not true. Okay, but for example, if we set B equals a single point, what does this mean? Okay, C0 is never 0, right? So that means 0 should not satisfy this inequality. And that means this index should be 0 index. Sorry, I guess I'm missing some signs. Okay, I'm saying that when B is a single point, index should be numerical. This index should be a negative number. Negative, so 0. Okay. And but this term class can be computed using parameterized using a single index zip for families. Okay, and you can express this in terms of M classes. Then some computation give you the desired result. So similar result that there exists some structures BI, CR. Well, I goes from I goes from BI belongs to page 4 of modular space of X. CI belongs to page 6 of modular space of X. Okay, these are some homological classes. Well, I goes from 1 to B minus of X such that this kappa classes kappa plus kappa P1A BE of this universal bundle equals some specific polynomial phi AB sum goes from 1 to 10 I. Okay, these are some specific polynomials which can be computed inductively. Okay, so what's the intuition here? Here, Pi, you should really think them as the second term class of this PVC. And the CI should be, you should think them as second term class of PVC. And the CI should be third term class of PVC. So the point is that if you have a projective line bundle associated to a vector bundle, these MMM classes can be expressed in terms of the term class of the vector bundle. And these polynomials are just some explicit polynomials. Okay, so then one get this result, then with some little more work, one can figure out that proof. Okay, so I think that's all.